Hello everyone, this is Rubika pursuing 3rd UG Mathematics at Ethridge College for Women. In this video, we will be showing that the shape of a uniform string hanging under gravity is a catenary. We will be exploring the mathematical beauty of the catenary curve in statics and its real-world applications. Now, the whole video is divided into 4 parts. In the first part, we will be understanding uniform strings and their properties under gravity. In the second part, we will be seeing what is catenary, its definition and mathematical description of the natural hanging curve. And in the third part, we will be seeing the real world applications of catenary as well as the parabola. And in the fourth part, we will be deriving the intrinsic equation S equal to C tan psi. Now, moving on to the first part. In this slide, we will be seeing what is uniform strings. A uniform string exhibits specific characteristics that determine its behavior under gravitational forces. These fundamental properties form the basis of our mathematical analysis. The 4 properties of the uniform strings are same thickness and weight throughout its entire length, composed of identical material composition throughout, length remains constant under tension, no stretching occurs, and its density remains uniform across all segments. Now we will be seeing what is tension. A tension is the pulling force in a rope or a string that acts along its length away from the object it connects. So from this diagram we can see the gravitational force will be acting downwards. So the tension is acting upwards to resist that pulling. This is called tension. So we have seen the properties of uniform strings. It has 4 properties: same thickness and weight, composed of identical material, same length under tension, and its density remain constant. So this is the property of uniform strings. Now we have understood the first part of the video. What is uniform string and its properties? Okay, now we will have a question. If you hang a rope between 2 poles, what shape do you think it makes? A straight line, a parabola, or a catenary? The answer is it forms a catenary shape. This natural curve emerges when gravity acts uniformly on a flexible string. Its shape can be mathematically represented by the intrinsic equation S equal to C tan psi, where S is the arc length, C is the constant, and psi is the angle of inclination. This equation only we are going to derive in this video. And what we have understood from this question, if we hang a rope between 2 poles, it will form a catenary shape. So now for that we have to understand what is catenary, right? So we are going to see what is catenary. A catenary is the natural curve that a flexible uniform chain or a cable takes when hanging freely under its own weight and supported only at its end. We have to note this line very carefully, that when catenary forms only when hanging freely under its own weight and supported only at its end. From this GIF, we can easily can understand what is catenary. This is the 2 ends and is hanging freely, supported only at its end. This forms a catenary shape. Okay. Now we will see where does this name comes from. The curve is named after the Latin word catenaria, meaning chain. It forms a distinctive U-like shape, similar in appearance to the parabola, but mathematically distinct. So we will have a doubt like, this looks like parabola. Isn't it a parabola? No, it is not a parabola and it is different. Catenary is different and parabola is different. The catenary is described by its intrinsic equation S equal to C tan psi, which relates the arc length, the angle of the tangent, and emerges from the physics of hanging strings under its gravitational force, right? So we will be seeing in the next slide what is parabolic motion. We will had a doubt, right? There is a difference between parabola and catenary. We will be seeing the difference in this slide. A parabola comes from a quadratic equation and describes the path of a projectile, like a ball thrown through the air. This involves initial velocity and follows ballistic trajectory principle. So, a parabola describes the path of the projectile. This is the main line. And in catenary, a hanging string follows gravity differently. Each point along the string experiences only gravitational force downward and the tension force along the string. This creates a fundamentally different curve. This is catenary. So in the catenary, we have already seen it will have a gravitational force downwards and a tension will be happening in that string. So a cat, because of its gravitational force of its own weight, it forms the shape of the catenary, while a parabola describes the path of the projectile. This is the difference between catenary and parabola, and there is a mathematical difference also. Parabola is given by y equal to ax square, while the shape of the catenary is given by the intrinsic equation s equal to tan c tan psi, and this equation only we will be proving in the upcoming slides. Right? Now we have completed the second part as well. Now we will be going to the third part. Where do we see the catenary? Catenary curves are hidden everywhere in our daily lives. From engineering marvels to simple household items, this mathematical curve appears whenever flexible material hang under their own weight. The first example is power cables. Electrical transmission lines naturally form catenary curves between poles, optimizing structural stability and material distribution. And we can see catenary in suspension bridge cables. The main cables of suspension bridges follow catenary curves, providing maximum strength with minimal material usage. And we can see catenary even in jewelry chains. Necklaces and chains naturally drape in quaternary curves, creating aesthetically pleasing shapes that distribute weight evenly. And then we can see catenary in hammocks also. See, we can see easily from the figure itself that it forms a catenary. When properly hung, hammocks form catenary curves that provide optimal comfort and weight distribution for relaxation. Now, where do we see parabolas? Satellite dishes. Satellite dishes are parabolic. This shape reflects all signals to a single point, making reception efficient. Rainbows. Rainbows show parabolic curves in nature. Light bending and reflecting creates this arc. So we have seen already that parabola describes the path of the projectile. So these have a path. A rainbow will form a path and it have a parabola shape. So that is the difference between parabola and catenary. We have few more examples for parabola. Roller coaster tracks. Roller coaster tracks follow parabolic curves carefully engineered for thrilling and safe rides. And even dolphin trajectories. A dolphin's jump follow a parabolic trajectory through the air. This graceful arc is a natural example of projectile motion. So from this we have completed the third part as well. Now we have moved to the final part, that is the derivation of intrinsic equation. We understand the physical principles behind catenary curves. Let's explore the mathematical framework that describes this elegant phenomenon, focusing on deriving its intrinsic equation. The derivation involves fundamental concepts from calculus, physics, and differential equations. Now, the derivation part itself we can divide that into four parts. First, we will be doing the force analysis, what is the forces acting on the string, and then we will be doing the fo- force balance equations, and then we will be relating arc length and angle, and then we will derive the final intrinsic equation. Okay, so before moving on to the theoretical part, I will just explain the diagram by part so that you can understand it very much clearer. Okay, now we are going to show that the shape of a string hanging under gravity is the catenary. So this is the diagrammatic part which I am going to explain part by part. First, this is a string. This is a tangent, and let's keep this as a violet color tangent. And then another tangent is kept on the violet color tangent, and this is a blue color tangent. And string. A string is kept on the two tangents, right? So a string is named A and B. Both the ends of the string is named as A and B. Now, a point P on the string touches the blue color tangent, and the point C on the string touches the violet color tangent. And we can see from the diagram itself that C is the lowest point, and Q is the intersection point of the two tangents, right? Then this is the angle between two tangents, and let's name that angle as psi. And S is the length of the CP. And we have already seen that how catenary curve occurs because of the gravitational force under its own weight. So definitely this thing will also have a gravitational force acting downwards. So I have kept an arrow mark for that. And then we are going to analyze the forces, right? So first, the tension T at P along the tangent, and then the tension T naught at C along this tangent, and then there will be uh, here the weight SW acting through Q. So we will be seeing this in more clearer version in this slide. I have given the same diagram which I have explained part by part here. So we'll be seeing one by one. Suspension points AB, the two points where the string is suspended, not lying on the same vertical plane. So this is the suspension points AB. Now C is the lowest point we have already seen, and then the point of intersection is Q, and then angle psi. The psi, what is psi? Angle between the tangents at C and P. And we have already seen, let CP, the length of CP be S. And then W is the weight per unit length. W, the constant weight of the string per unit length, making the total weight of the segment CP equal to SW. Let W is the weight per unit length, and CP has a length of S units. So 1 unit is W, means S units will be SW. That is how the weight of the CP came as SW. And then we are making the force analysis. What are the forces acting on it? The first, the tension at P, the tension acting at point P directed along the tangent and inclined at an angle psi, and then the tension at C, T naught, the tension acting at point C directed horizontally along the tangent, and the weight of the CP SW, the total weight of the string segment CP acting downwards through point Q. Now we will having the equivalent length C. What is equivalent length? The length of the hypothetical string segment whose weight is equal to the horizontal tension T naught. So we now from this slide we can see that T naught is in horizontal and SW is in complete vertical, but T is in slanting. So we have to, and it also have an angle. So we are going to resolve these two. So by resolving, we will get, like in the horizontal, we will get T cos psi, and in the vertical, we will be getting T sin psi. That is what given here. Resolving tensions T into components. At any point P on the string, the tension T can be resolved into horizontal and vertical components. Tension horizontal, that is why horizontal is represented as H equal to T cos psi, and tension at vertical is T sin psi. Now the third part, we are going to equilibrium condition. Use equilibrium conditions. For a segment of the string CP, the lowest point C to a general point P, the forces must be in equilibrium. The vertical component of tension at P balances the weight of the string CP. Here T cos I acts, and here T naught also acts. So we can equate them. And also in the vertical side, here SW acts and here T sin psi acts. So we can equate both of them. So the horizontal component of tension at P balances the horizontal tension at the lowest point C. This gives us the following equilibrium equations. T sin psi equal to SW and T cos psi equal to T naught. Now we are going to derive the relationship between S and psi. Dividing the vertical equilibrium equation by the horizontal equilibrium equation eliminates T. So we are going to divide these two equations and T will be get eliminated. We will be getting sin psi by cos psi equal to SW by T naught, and sin psi by cos psi is tan psi equal to SW by T naught. So from this we are going to take only S and making all the other variables on the other side. We will be getting the length of the string segment S as S equal to T naught by W tan psi. Now we have already seen what is equivalent length. The equivalent length represents the length of a hypothetical string segment whose weight is equal to the horizontal tension T naught. So we can take C as T naught by W. So substituting this C in this equation, we will be getting S equal to C tan psi. This is the final intrinsic equation, the derived intrinsic equation S equal to C tan psi. This equation represents a catenary. That's why the shape of a string under hanging gravity is a catenary. The derived intrinsic equation S equal to C tan psi fundamentally defines the catenary curve which describes the shape of a uniform string hanging under gravity. This elegant relationship, where C is the equivalent length, highlights how the catenary is a natural form in engineering and nature. That's all. From this video, we can able to understand why the uniform string hanging under gravity forms a catenary shape, and we have seen what is catenary, and we have seen the difference between catenary and as well as parabola, and we have seen the real life examples of catenary and the real life examples of parabola, and also we have finally derived the beautiful catenary intrinsic equation, that is S equal to C tan psi. By this, we can mathematically prove that the shape of a uniform string under gravity is a catenary. That's it. Thank you so much.